Good afternoon. This is CIVE632, Computational Hydraulics and Hydrology. And I am going to, this session is the second session in the fourth week, and I'm going to be talking about in extensive detail, about the Muskingum-Cunge method. Today we are going to hopefully cover at least 4, if not 5, and finish up where we should be finishing. I'm going to first be talking about BO5, the Simplified Muskingum routing equation. This is an invention that we came up with at about that time in the late 70s. It's kind of nice. It's playing around with the numbers, and it's nice. I have received, every once in a while, I receive some good comments on this method. At this point, I would say that while it's nice and it shows the power of the methodologies that we're working with, it is kind of too simple, and you'll see it, okay? You'll see it in a minute. But it's there to the understanding, for understanding of this process that we're going with. Then BO6 is variable parameter Muskingum-Cunge revisited in 1990, oh, I forgot to put the date in there. I think it was 1994. Chaganti was one of our students, and I tasked him with doing this work, and he did a great job. And we revisited the variable parameter and increased its accuracy. Then BO7 is the Thomas problem in online computation. Marcela Diaz was our student in the year 2016, and I also again tasked her with, because the students have to do some work, you know, for grade. So I told her to do a calculator of the Thomas problem, which had not been done. Certainly online has not been done. So basically the Thomas problem has been totally completed, not totally, but to a great extent, done with a calculator. And I'll demonstrate the use of the calculator. And then the last one is Muskingum-Cunge amplitude and phase portraits. At the same time that Marcela was with us, there was a lady from India. Her name was Vavia Bupalapati. And I first asked Vavia, well, they were going to do special studies with me. So I first asked Vavia if she was a math wizard, and she said she was. I believed her, I trusted her. You know, the people from India have a way of showing that. I said, well, okay, cool. Then I'm going to task you with something really, really complicated. And I did, and she did it. She did it beautifully, and we came up great, smelling like a rose on this project. And finally, hopefully, if I have time, if not, I will briefly talk about it next week. The Ferrick paper. I am in love with the Ferrick paper because it opened my eyes on the issue of dispersion back in the year 1984, 85. And then we had to wait actually a little bit more. Then we had to wait a number of years for me to digest all this information. I believe in 1989, I came up with the true study of dispersion, because Ferrick had done it. Ferrick had introduced us to the idea, but like any very good researcher, I already told you, he didn't complete the job. He left it halfway. And so I saw the opportunity to write a paper, because that's what we wanted to do at the time. So we wrote a paper on the completion of the Ferrick theory, of the Ferrick dispersion theory. And the problem was that Ferrick did not know or could not non-dimensionalize the equations. We could, because we had a lot of experience with that. So therefore, we improved the Ferrick treatment, and I'm thankful to him for allowing us to complete his work. We actually completed the work by Ferrick. So right now, I'm going to go on the simplified Muskingum routing equation. Is everybody seeing the green sheet?
Yes.
Okay. Yeah. Okay. So this is simplified Muskingum routing. So the Muskingum routing of Cunge, we are going to simplify it. It's already simple, but we're going to simplify it further. Okay. The Muskingum method and its variations are well established. The parameters K has been determined by calibration. That's the Muskingum. But an improvement of the Muskingum is the Cunge method, who showed that the parameters K and X could be related to the physical problem. Correct. Everybody knows that. With the aid of Cunge findings, the calculations can proceed either in a lump parameter mode, that means establishing an average flow value on which to base the calculations of the routing parameters, or you can go nonlinear. The nonlinear gives you more resolution of the problem, better, somewhat better, but it comes at the cost of very small percentage of mass loss. The reason is because we are off-centering the derivatives. The values are off-centered slightly, a little bit. And every time you off-centered something in numerical analysis, you pay a price. And we had no other way of doing it, so we did it. We did it first in the year 1978, and we already looked at or talked about it last Monday. And then in the year when was this paper? 1990. Oh, there's a mistake in here. 1994, I think it was. No, I take that back. I'm totally messed up in here. It was 79. This is correct. The original version was 79. Here, there it is. Technical version, numbers 79. If you go in here at the bottom, it says 79. Yes. Yeah, I have to undo myself here. In a year later, 77, 78, 79. A year later, we did this. It was easy, and it was the thing about this, important thing about this methodology is that we ended up basically kind of mimicking the Kalinik-Milyukov method without really wanting or knowing. This is luck again. Because the Kalinik-Milyukov method is based on this on situations similar to that. But of course, we don't have to review the Kalinik-Milyukov method because, I mean, why? We already have the tool, the perfect tool. Actually, a tool and then a simplification of the tool. So, and I can tell you repeatedly for the nth time that the Muskingum method works, and it works perfectly. And why does it work? Because it always shows grid independence. Grid independence. And the only thing we want in a methodology is grid independence. Well, not the only thing. We want grid independence, and we also want accuracy. But the accuracy has already been proven. I already told you last Monday how we figured out that if we use the theory and we use the numbers, they ended up with the same number, the same answer for the routing problem. What is the routing problem? The routing problem is to follow up the progression of a flood wave along a channel. That's all the routing is. And what actually happens is the flood wave moves with a celerity, which is technically the celerity of Seddon, the kinematic wave celerity, and then it does attenuate. And the attenuation depends on the size of the wave. If the wave is kinematic, according to procedures, it should not attenuate. And if the wave is diffusive, it will attenuate a little bit. The British, in their famous flood studies work of 1975, that I've quoted repeatedly, had said that if the diffusion was within 30% after one propagation period, that it was supposed to be or could be considered to be diffusion. And if it was more than 30%, then it would end up being a little bit more dynamic. I mean, because dynamic is supposed to dissipate immediately. So if the wave dissipates 100% within one propagation period, it is dynamic, right? But most waves do not dissipate. They dissipate a little bit. So Price was right, or the British were right when they said 30% is a good number. Now, what is one propagation period? That's a mouthful, but it basically means when the period is reproduced downstream. The period, say 24 hours, you reproduce like you move the wave downstream a period in a wavelength and a period related by the celerity. So that's where we could normalize the measurement of the attenuation. So let's keep moving along in here. These equations are, you already know these equations. We have repeated them extensively. Okay. In equations 2 to 4, in equation 2 to 4, if delta t over k and x are specified like that, there's a mistake in here. I should fix it. I'm going to write it down. There's a zero in italics, which it shouldn't be italics. The numbers are not italics. Let me write it down. Okay. It follows that C1, C2, C3 equal 1/3. In other words, for the special case of Courant number equal 1 and Reynolds number equal 1, D equal 1, we end up with the three coefficients of the routing being equal. So all you needed to do was to take the fourth value on the right top as being equal to the average, the straight, simple average of the other three values. How simple could that get? That's equation 8. That's fascinating, actually, how the numbers could work out this way. Therefore, we have the Courant number and then the cell Reynolds number. So if we set the Courant number equal to 1 and the cell Reynolds number equal to 1, all we need to do is to take an average. And that's nice because this could give you a quick way of doing some routing. Very quick way. I mean, you can do it simply in Excel. Um, but in order to do that, you got to figure out what the delta x and delta t should be. And these are given by equations 13 and 14. By definition, follow from what I just said. Okay, and then we insert for practical applications, we got to come up with 16, 17, and 18. I told you, I always review the class before it happens, like in the morning or the afternoon, the day of the class. And I check the algebra and all works fine. Because I don't want to put myself in a situation that there was an error, then somebody asked me about an error and I can't fix it or I don't know. And on the spot, it's hard to figure things out. So I can tell you off the bat that equations 16, 17, and 18 are correct. And if you want to verify it, welcome. Go ahead and do it. You should, just for the heck of it, or practice, right? So the model testing, the testing of a mathematical, this is a very important place, a very important, how can I say place, not place, section of this paper. Extremely important, because this is where a lot of people miss. So model testing, the testing of a mathematical model usually hinges upon whether the model can reproduce measured field data. In other words, most of the modeling we do nowadays is mathematical. Like 50 years ago, when I got started in my career, a lot of the modeling was physical. The country set up physical laboratories in order to model by using similarity, laws of dynamic similarity, etc. And I do not believe those things are taught at this time because the physical model laboratories are fading away. But every country had their physical labs. Just about every country worth their salt, I guess. I don't know. There's 200 countries. I don't know. I wouldn't say that there are hydraulic physical labs all over the world. But certainly there are in the United States, in Europe. Portugal has a big one. Spain also has a big one. CIVE632 in Spain. I don't know exactly what Portuguese call them. I've not been to France ever. I don't think I'll ever make it over there. But they do. They always advanced countries have physical laboratories or had physical laboratories, and but the physical laboratories are fading away. In Peru, they put together a physical laboratory in the 60s, early 60s. I actually worked. One of my first, if not my first job, was in the lab out there, in the hydraulics lab, back in the year 1966. That's how many? I was 20 years old, exactly. So at any rate, the point is that that hydraulics lab is not really operating. It's operating, but it's operating just because they don't want to kill it. But I mean, they really have very little activity, I think, at this point. At least certainly not the activity that they had 50 years ago when they started. So long story made short is that physical laboratory has been put aside and is now the numerical laboratory has taken over in the last 30 years since we have become capable of doing this because the computers were getting better and better. Nowadays, we got the most fantastic computers. Okay, so we have, when discrepancies occur, like if you do a calculation and you have a measured data out there and there's a discrepancy, so then you wonder, did I mess up or is it the data? Okay, when discrepancies occur, it is very difficult and sometimes impossible to determine whether they're due to errors in the numerical solution. And we're here to study errors in the numerical solution. If anything, when this course is finished, you will understand and you will know how to pursue this subject. In the numerical solution, in the estimation of the parameters that we plug into the models, like the Mannings, could be wrong. Or any other parameter that we put in there, in other model. In our work in flood routing, the parameter of choice or the crucial parameter is the Manning or the Chesney. Well, most cases is the Manning. Also, the cross sections. If we got to put it there, the cross sections are wrong, then the model is going to be wrong. But at any rate, that stuff is the estimation of the parameters. Or thirdly, in the measured data. If procedure currently open to question, and this is where I stand strong here, consists of lumping all these errors into one and adjusting the model parameters to fit the measured data in what has been referred to as calibration. You mix apples and oranges and peaches and so forth, and then you get out an answer out of the hat, and that's it. That's the answer. That is not correct. Okay. A sounder approach consists of isolating the sources of error in order to study their effects separately. That's why we insist that when you develop a model, you should test stability and convergence first. First, stability, because without stability, you got nothing. But once you have stability, you could still have non-convergence. And therefore, one should be confident, a modeler should be confident that you're doing the right thing from a numerical standpoint. And for that purpose, you got to understand what we're going to teach you this semester. This is done by performing both a hypothetical test and a real data test. The hypothetical test is designed to isolate the effects of numerical accuracy in the model results. In other words, we're going to take an example for which we know the answer, and we're going to try to get the model to do it. If the model cannot do an example that is clear for which we know the answer, the model's no good. Then we've got to find something else, or we got to find its properties of stability and convergence. On the other hand, the real data test is designed to provide information on the accuracy of the parameter estimation. Yes, the parameter. The parameter could be wrong. The Manning's n could have been too high or too low, the estimation. The only way to correct the Manning's is to actually do a measurement. And nobody does that. I'd say less than 1% of the people that are out there working are doing measurements because they're expensive, they're cumbersome, they're trouble. But we can estimate. And estimating Manning has become the bread and butter of hydraulic engineers. We do it all the time. I don't lose any sleep on it because I am confident that what I'm doing is the best can be done at the time. But if you're not expert or not geared or stepped in the situations, then you'll have a little trouble at the beginning in estimating Manning. But for that purpose, of course, you have a lot of help. You get the child book, the Barnes book. The Barnes book is good, which I talked about in my course in hydraulics, open channel hydraulics. The Barnes book is good, and practice, nothing beats practice. Okay, so we're going to do a hypothetical data test. Hypothetical test using the classical example of Thomas. Why we use Thomas? Because we like Thomas. Was set up to test the method proposed. The following two runs: a test run using the simplified method, which is the method that we're proposing here in this paper, and a control run using the conventional method, the one that I already talked about in the last Monday. In the test run, x was made equal to 0 and k equal delta t, which is exactly the way it's supposed to be. And accordingly, the space and time intervals were calculated to be delta x 13.5 and delta t 2.116. Note that here we did not choose out of the air the delta t and the delta x. They were calculated by the formulas of Cunge. In the control run, meaning the test to see if that works, the space and time intervals were specified arbitrarily to be 25 miles and 6 hours, which is what I have specified for you for your homework. This resulted in x and delta t and k, and these are the values of the Thomas problem: base flow 50 CFS, peak inflow 200 CFS, reference flow 125 CFS. This method is approximate. It's an approximate method anyway. The linear method is approximate. So we're justified in taking 125, which is the average. I, at one time, thought about finding the center of mass, something like that. But I figured that wasn't going to improve a whole lot because this is an average method anyway, because it's a linear method. And the world is really nonlinear. We already shown that. Okay, calculated results for peak outflow is 177 and travel time 128. Those are the numbers that you should be shooting for when you do your Excel problem. 176.5 actually. Okay, so the real data test. So then we set it here. We're going to do the real data test, and I'm going to speed up a little bit here, otherwise we won't finish. The real data test, we had some data that was contributed by Professor Cheng, who was my colleague at the time at Colorado State. So we got the data in here for the real data, and we ran the implicit method. The implicit method is the method of Danny Fred. Of course, Danny Fred wrote the implicit method in 1973, but he was not the only one that did it. Chen had it done. I had it done. Professor Chang, who for 40 years taught at San Diego State from the 60s to the 2000s also had an implicit method, which he called fluvial. Fluvial 11 was Professor Chang's model. So there's a few implicit methods out there. We use, I believe this was our own implicit. We ran our own implicit. And we came up with these answers. Number one is the inflow. Number two is the observed. Observed at Goldsboro, observed at Kingston. This is in North Carolina. The three is the implicit method, and the four is the simplified method, the simplified Muskingum. In other words, for those of you that are still wondering what the heck's going on, okay, the implicit method did 100 times more computation than the simplified method. The simplified method took the Q's and took the average and ran with it. The implicit method had to do all kinds of rigmarole in order to get to the answer. And the answer was pretty much the same. Why? Because both these ways were kinematic. They were kinematic. And our method is Muskingum-Cunge, follows the kinematic as long as it's properly posed, right? So we basically showed, we also said something, that the lateral inflow could not be ascertained. I don't believe anybody out there can ascertain the lateral inflow. What's the lateral inflow? The lateral inflow is the base flow that's coming in or out. In a wet area, the base flow is positive. It's coming in, always. In a dry area, the base flow is negative. There's immersion of the flow into the channel. So therefore, we estimated just ballpark estimate, 0.01 cubic feet per second per foot on this particular river. I don't recall the name, but it's there. And that gave us these results, which were considered to be nice. Okay, so none of the methods can reproduce exactly the measured hydrograph. And this is what I'm saying. Routing is an art, but it's an art, really. It's not a precise calculation. There's all kinds of ifs and buts. The reason for this lies in the uncertainty regarding the amount of lateral inflow, which is likely to be time and space dependent, at least space dependent. Okay, table 1 shows a comparison of the results, time of passage, okay. In view of the uncertainties involved in the estimation, the results of the simplified method are certainly within reason. Basically, I said, we did 100 of the calculation, we ended up with more or less the same answer. Simplified methods belong to the family of diffusion models, etc. And in here, this appendix is going to help you do your homework, not this one that you're working on now, or that you're going to be working for the next 2 weeks, but the next one. So I'm just going to leave it there, and I'll get back to this later on. But you got to come back to this page in order to solve the problem of homework number 4, or problem number 4, I believe. I'm confused here. I believe it's problem number 4. Okay, so I'm going to leave it there, okay, and I'm going to come back to this now Chaganti paper. The Chaganti paper was done in the year 1994. I had come to the realization that there's various ways to calculate the variable parameters. And the way I had done it when we did this in 1978 was very rough. So I said, well, maybe I should improve this. So I convinced Chaganti to do this project. All the students that have worked with me over the years have worked on projects like special studies, right? Because they usually spend a couple, 3 months on this. It's not easy to immerse yourself in this stuff just cold and do it in a week. No, that cannot be done, okay? So Chaganti did all this work for us, for me, and so forth. We worked together, and we basically tried to come up with a better way of calculating the variable parameters, and we did. We improved about halfway, like 50%, and you'll see it in the numbers. We say in here that you can choose linear or you can choose nonlinear. The linear gives you simplicity, the nonlinear gives you more accuracy in the estimation of the steepening. But of course, the steepening is small. The only reason why we show a lot of steepening is because we route this wave 500 kilometers or 500 miles just for testing purposes. Nobody's going to route a wave 500 miles without intervening lateral inflows, like another river coming in the midst of it and resetting the whole process up, getting the whole kinematic wave up. So what we're doing is actually laboratory testing. We're in the laboratory, we're testing the behavior of these methodologies. We're not in practice yet. We're learning how these methods work. Okay, so this paper revisits the variable parameter of Ponce and Yevgevich, 1978. So we confirmed the small but perceptible loss of mass. And here we go into the background, and the background is the same. Developed by Cunge, the method, the Muskingum-Cunge method, and documented in the flood studies report, which I've quoted many times. We express the routing parameters and so forth. And we also say in here, the method was adopted by the most recent version of the U.S. Army Corps of Engineers HEC1 model. I should refer you to the history because I had lived it. In 1982, we released our linear diffusion paper, of which I already talked about last Monday. In 1985, 3 years later, SCS came up with the thing, oh yeah, we got this thing squared away. We talked to Professor Ponce and he gave us the method. In 1987, Army Corps was jealous about it and they said, hey, I mean, SCS is getting ahead of us. Let's call this guy Ponce. After all, he's right here. He's in San Diego. San Diego, Davis, it's 1 hour. Okay, so I went over there and together with Danny, because there was an issue out there, and explained to them what I had done. And then in 1990, 3 years later, they reissued the HEC1 version model on its version 4 because it had 1968, 1973, 1979, and 1990. 1990 was the version 4 of HEC1. In 1998 was the version 1 of HMS. That's the history of this whole thing. Okay? So, so the method was adopted by HEC1, and bless their heart, they quoted me all over the place. Yeah, they quoted me. They said, well, you know, these methods were developed by Cunge, but they were pursued here in the US by Professor Ponce. So if you go to HEC1 and HMS, not HEC1, nobody goes to HEC1 anymore. If you go to HMS, I'll be quoted in those pages they talk about the routing and how we did it and so forth. So these are the equations. Interestingly, though, my C's and D's disappeared somewhere, somehow, in the shuffle. They disappeared. They don't appear in the HMS. I think that's a mistake of them, but that's their mistake, not mine. Okay, because I think the C and D's provide clarity. Okay, so these are the C and D's, and you already know this. We already talked about this. And then we go to the numerical experiments. We're going to use the Thomas method because we believe that's a ruler, right? So we use the Thomas method, which is given by this rating equation 8, which is point Q, lowercase q, discharge per unit of width equal 0.688, and the depth to the 5/3, which already because of the 5/3 is telling us that that this is a unit with channel, and the 0.688 comes from the fact that the slope, because the slope it's a kind of the conveyance. The conveyance value is 0.688. It comes from the slope and from the Manning. Okay, and you should redo these calculations because it's part of your homework. You should verify that the number is 0.688. I wouldn't take it, I wouldn't take it just off the bat. This amounts to a Manning 0.0297, the back calculation of the Manning. You can back calculate the Manning too. So we use the following method: the constant parameter for reference, the 3-point variable parameter, which you already established, the iterative 4-point variable parameter, and then we came up with the new methods. In the new method, the difference is that in the normal procedures, we were calculating the Q from the grid and the C from the grid. You can see that, the Q and the C from the grid. While over here, we were calculating first the Q from the grid, which is the important value, and then we were using equation 7 to calculate the C. Equation 7 is over here. There it is, C. Okay, in other words, it was slightly different and better. Better because we were using only one value from the grid. The other value was based off the grid. And that led us to an improvement. I'll show you the improvement. 2 resolution levels, results. Okay, here's the improvement. Okay, you have 2 resolution levels, Roman 1 and Roman 2. We have 3 base to peak flow, 4, which is 50 to 200, then 10, which is 50 to 500, and 20, which is 50 to 1000. The peak is 1,000, the base is 50. Why did we do this? Thomas never did that, by the way. Thomas restricted himself to 200. We wanted to force the issue because we knew from experience that the better numbers were going to be the the number 4 was going to be better than the number 10, and the number 10 was going to be better than 100, than 20. So I said, I'm going to force this all the way to 20, so nobody can complain that I didn't do it. Okay, you used 200, but I mean, what if you use 1,000, right? So we used 500 and 1,000, and sure enough, we were correct. Look at the numbers here. 99%, 99.5, 98.8, 98.4, slight improvement. Never mind that this is at 500 miles. So, I mean, since nobody's going to do 500 miles, most people are going to do 50 or even 10 miles. This number 98 is going to go to 99.8. So it's perfect. It works fine. It works fine. In this resolution 2, just to make sure that the resolution was not a problem or a factor, we did that for the 2 resolutions. Easy to do in the computer. And we got all these numbers. And as you can see, all 5 methods give approximately the same peak and time to peak. The ratio of peak outflow to peak inflow is approximately the same for all 3 peak inflow to base flow ratios. This suggests that the wave diffusion is independent of the QPI over QP ratio. The constant parameter conserves mass exactly 100%. That never ceases to amaze me, how handling all those numbers, integrating all that stuff numerically, we integrate numerically, we didn't integrate analytically. You could integrate analytically, get a right answer, and then bingo, you get an answer. That's kind of cheating. Numerical is harder, and yet we were getting 100. Look at this. Look at this. 100. 100. It never ceases to amaze me. I think numerical hydraulics is a beautiful field, really. It's so well behaved. Okay, so the constant parameter conserves mass exactly. The variable parameters do not conserve mass. But don't be afraid, because it's very, very small amount, something that it could be masked by the normal inaccuracies of the method. The loss of mass is cumulative and can be assessed quantitatively. The loss of mass is greater from the 3-point methods than for the 4-point methods. That is understandable too. The loss of mass is greater for the conventional methods than for the modified methods. That is also understandable, given the fact that how we did the second evaluation as opposed to the first evaluation. The loss of mass increases with QPI over QV ratio and does not appear to be strongly related to resolution level. Okay, it should be noted, this is important, it should be noted that the mass conservation percentages shown in table 7 or column 7 of table 1 are cumulative values for the 500-mile reach for the Thomas problem. Thomas actually used only 200 miles, not 500. We try to stretch it, force it. A typical flood routing application normally not considers such long reach without intervening lateral inflows, which would tend to mask the accuracy of the computation. Reset the problem, start again. Never mind that you were making an error, forget it. Now it's reset. Therefore, the percentages shown should be interpreted as an extreme or worst case scenario. Figure 1 showed a set of hydrographs. And look at this in here. The hydrograph for all the methods looked the same. We couldn't plot the difference. It was so close. Okay? In the scale that we were using, the inflow is this sinusoid over here, which it's up to 1,000. We showed the 1,000. The outflow is, for the linear method, is that the constant parameter Muskingum, it's this one, which is a sinusoid too, translated by nevertheless a sinusoid. And then the actual nonlinear method, which, like I said, all 4 values were distinct, different, but they all get plotted in the same place because they're so close, according to the scale that we were using. Both the modified and the variable parameter plotted in the same way. And as you can see, these come up with what has been referred to as the gamma function, or it's not a total sinusoid, it's an imperfect sinusoid. Why? Because of the nonlinearity. Now, in the real world, those hydrographs look like this. Look at nonlinearity. Okay? But then there's a question is whether the nonlinearity in the real world is given by the different speeds of translation or transport of the three components of the flood hydrograph: the surface flow, the subsurface flow, and the groundwater flow. And we don't know that, and I'm not going to get into that because that's huge problem. But it doesn't really matter. The point is that in practice we have these shaped sinusoids, and in theory we can talk about sinusoids forever, but you cannot find a sinusoid in practice. I shouldn't say that strongly. It would be hard. It would be hard to find a sinusoid, a perfect sinusoid in practice. The hydrographs look more like the ones shown in here. So the conclusion is that we improved a little bit. So if you wanted to do the variable parameter, that you'd be advised to use the second method as opposed to the first. That was an improvement. So we finished in there, and now we go to the Thomas problem. The Thomas problem in online computation. This is the paper, the work that Marcela Diaz did for us, and there's a video in there. I may show it later, depending on whether we have time or not. We're going fairly smoothly in here. The Thomas problem in online computation. We had the Thomas problem nailed down for many years, and I asked Marcela to come up with a calculator. She wanted to do that. It's not easy, but it can be done because technically I'm right next to her. So if you make a mistake, I can help her fix it. She worked on the lab for about a year and a half. Actually, almost 2 years, I think. Yeah, it was 2 years. It was 2015 and 2016, and she got a master's working in the lab and finishing up her classes. She and Vavia and a couple of other and another person were actually working at the same time in the lab. They all graduated at the same time. There's a photo opportunity or a photo of that graduation at the end of the year 2016. Okay, here we go again. The Thomas problem, classical problem of flood routing. Thomas routed a sinusoidal wave through a unit width channel of length 200, and we routed it to 500. This is the Thomas problem that you are going to be working with in your homework starting today. And it's due the 29th. It's due in 2 weeks. I gave you 2 weeks because I wanted to give you ample time because it can be tricky if you have never done it. I mean, if it's easy if you've done it 10, 100 times like we have. The base flow QB 50, the peak inflow 200, the time base of the hydrograph is 96. Suffices to say at this point that the time base of the hydrograph controls the kinematicity. If it's 96, it's less kinematic than 192, and if it's 48, is the wider the TV, the more kinematic the wave is. So 192 is more kinematic than 96, and 96 is more kinematic than 48. Therefore, 48 should diffuse more than 96, and 96 should diffuse more than 192. And 384, which is double the 192, which we didn't test, should diffuse hardly anything because by that time you're getting all the way to kinematic. It can be shown that. So in this paper, we describe an online calculator for the Thomas problem using the Muskingum-Cunge method. What I wanted to do in here was this. My objective was this: to get a tool, an online tool, which people could actually test to see what diffusion of a wave was. Because I already told you a minute ago that depending on the TB, you get more. If the T is greater, you get less diffusion, and vice versa. And people that are beginning to do this should understand that that is the case. And I advise you to run this model several times. You're going to spend 1 second running it, right? So it won't take too long to get a lot of answers so that you can analyze what the response is. Unfortunately, we did not plot these because, funny as it may look, we dropped the ball and we never actually came up with a plotter. That's on my things to do, but honestly, I don't think you'll get done. I need somebody that really knows PHP in order to do that. And I claim I know, but I really don't know. I may know 20% of PHP. PHP is a huge thing. PHP is the driver of the web. Google and all these other people use PHP in similar programs. So you got to technically be a computer software person in order to really handle it. We have them. It's just I have not come across anybody that could do this work. So I really honestly don't know, and we just give the numbers out. We don't plot it. If one wanted to plot it, all it takes is to cut and paste from our report and plot it into Excel, or put it into Excel and plot it, because Excel is very adept at doing that. Okay, so we have the methodology in here. I repeat the equations, I repeat the graph, I repeat here the RCD equations, the Curran number, the cell Reynolds number, the discharge rating, the flat wave celerity, that means the Seddon celerity, beta times Q over D. Q over D is the velocity, the mean velocity. Beta is the exponent of the rating, which, as you know, for Manning is 5/3 and for Chesi 3/2. And the constant for Y channel. Mind you, at this point, those numbers are not fixed, because if the channel is not wide, if it's trapezoidal, or if it's triangular, or God forbid, if it's the inherently stable channel, then the beta is going to change all over. Actually, the beta has two limits. It can go as low as 1 and as high as 5/3. If it gets about 5/3, then you're running into cases of the Horton problem, which is typically in overland flow. And if you run even higher than that, you can run into the Izzard problem, for which the beta, R beta, which is the C in that problem in the paper that we talked about Monday, gets up to 3. Remember 3, the number 3? Okay. I read the Izzard paper, and I was really surprised when Izzard started talking about equal 4, beta or C, same thing. He used the word C, we use the word beta. People use different things for the same thing. And he was talking about 4, and I was really surprised. And he did not quite explain. He just said that he thought 4 was a good number. I honestly have a hard time believing that. Why? Because the laminar flow is kind of a ceiling, and laminar flow is 3. And white flow is a ceiling too. We know that, meaning it cannot go above that. So it's hard for me to believe that exponent of the rating could go above 3. However, Izzard was talking about it. He must have known something that we do not know. But I think the variation of C or beta is between 1 and 3. Wait, there is a caveat. Can the C or beta be less than 1? And the answer is yes, absolutely. If you run into a situation where you have a culvert where the flow closes on itself, like in a culvert, the round cross section, at that point you will get a beta or a beta, say, less than 1, 0.7, actually 0.9, 0.95. That can be calculated, by the way. And Chow was the first one to say that. It's in Chow's book, somewhere in Chow's book. Chow's book is a thick book, 500 pages. You will have a hard time finding it. But somewhere in Chow, it says that exponent of the rating could be less than 1 if you run into a situation of a culvert flow, which is correct, by the way. We have done those calculations. Okay, so we got in here in the constant parameter, calculator of the average distance, the Thomas problem. We already know the Thomas problem. Repeat it in here. For consistency, the value of n can be back calculated as 0.0297, the online calculator. So what this calculator does is that it sets up the Thomas problem data on the basic cell of Muskingum, which we already know, Muskingum-Cunge. And it varies the length, 2 lengths, 200 and 500, which says those are the Thomas length and the extended Thomas length. Then a choice of peak inflows, 200, 500, and 1,000. 200 is the Thomas peak inflow, and the 500 and 1,000 is our extended Thomas peak inflows. Notice that this choice provides a peak inflow to base flow of 4, 10, and 20. We already gone that through in the previous paper. A choice of time base, 48, 96, and 192. 96 is the Thomas problem. 48 is a little bit less, more diffusive problem. And 192 is a little bit more, double, more kinematic problem. The time-based multiplier, we had to get a time-based multiplier in order to route the program. So to determine total simulation is 2.5. We figured that was enough to route the hydrograph to see the downstream flow and not to cut it in the middle. So we put 2.5 in there. We could have put 3 also, 3.5, but 2.5 sounded like a very good number for this. Therefore, the corresponding values of total simulation time, we call that, the total amount of simulation, not has really nothing to do with, well, not really nothing to do. It's kind of related, by loosely related to the T. And you know the T is 48, 96, and 192. So this had to be 2.5 times each one of these. 2.5 times we figured there was enough diffusion in there, but not so much diffusion so we could pick up the tail of the outflow hydrograph. We don't want to cut it in the middle. Therefore, we have the hydrograph in here, the table, input data, routing, and so forth, 18 possible combinations of all the we have run, right? We have the runs for length, peak, length 200, 500, peak 200, 500, and 1,000, peak 200, 500, 1,000, 4, 10, and 20, right? And then we had all these values that we had to set up judiciously, carefully. It's not just any number. We got to set it up. For one thing, the Qur'an number needed to be set around 0.1. I'm sorry, 1.0. Because if we didn't, it was going to mess up. We know that for a fact. It does. There's not a very rigid. It could be 0.75 and it will work. It could be 1.25, it will work. Okay, and in the D, we didn't have a whole lot of intelligence, but we knew that it was on the order of 1 or less than 1. We'll talk about this in a minute later in more detail. The C, as you can see, the C's were picked up so that you will get around 1. Some of them were really 103. Then the D, then the total simulation time, we already explained to that. In the NT and NX. Oh, the NT and NX is the number of points, 80 and 16. And then in the discretized map. So we have an example here. Run example, an example for use of the calculator. We're going to run the standard value. L equal 500, Q equal 200, and T equal 96. That's the Thomas problem. So that should come out to 176. And it came up to 176.84. It's on that order, 176.5 on that order. The question, of course, well, really, we shouldn't be picking up, saying that what is the exact number to the 5th decimal. In engineering, we don't even get to the 3rd, let alone the 4th. So 176 should be okay, but we came out with 176.84. Comparison, the analytical results that I already shown you last time was 176.74. So in 127.82, so they were very close. So that means our calculation, our PHP calculation, our model was a good expression of the actual thing, and you see it in there plotted directly from the calculator. This was plotted directly from the calculator. So I'm just going to go in here and just run the problem for you. Okay, this is easy to run. Name, test. I'm sorry. Test 2109. Today's the 15th, right? And the time is 1817. Okay. I'm sorry, that's not the time, the date. Name, test, date 210915, 1817. And I'm going to choose 11 for the heck of it. Okay? And we're going to do the calculation. How long did it take? Less than a second. This is easy. Easy for my computers, my servers are very powerful. We do the dissolve, I'm sorry, not the dissolve, the Sacker, which is 20, 30 million calculations in 2 seconds. This one, maybe a couple thousand at the most, calculations, products. So there it is. You can take this and plot it into Excel, and that's what it would come out. So that is the Thomas problem with online computation. Let me see. This video is only 11 minutes. So I'm not gonna show it. I'll have you look at it later. We'll show it if we have time. I don't think we'll have time. We'll see. The Promise problem has a video, which we basically told everything I have already repeated to you in vectorized form, in vector, meaning in equations, right? I use the word vector for equations and raster for everything that is video. Like a video is a raster. A paper is a vector. Okay. So now Sit tight and hold to your seats. Why did I say that? Because we are going to enter into unknown terrain in here. It's going to be amazing, really. If it's not amazing, you let me know, because I don't want to talk falsehoods, okay? So we're going to head in here to Vupalapari's work, which was, of course, we worked together on this. I believe I had already done this, but we didn't put it on the web yet, because when we did this 30 years ago, there was no web around there. So I wanted to Vavia Vupalapari to confirm. Now she's working on San Diego, one of the companies in San Diego. Bavia said, I told Bavia, I said, you check everything I've done, I'm going to check it too, and then you plot it, and then you write the computer program, and I'll check it and so forth. And since we got experience, if you make a mistake, it will probably show. Okay, so, because there's a lot of computation in here. So here we go. Like I said, sit tight. Muskingum-Cunge amplitude and phase portraits with online computation. Now, what is an Muskingum-Cunge amplitude and phase portraits? Okay, the first gentleman, to my knowledge, that was talking about this was Lendertzy, that in 1965 wrote a paper on the computation of two-dimensional flow in oceans. He was doing a two-dimensional model for ocean flow, coastal flow. That's what we're interested in. And he was at the beginning of this work, or this area, and he felt compelled to analyze the stability and convergence, because he knew that it needed to be done. Anytime you develop a model from scratch, you should analyze the stability and convergence, because you can run into all kinds of dark alleys and not get out of it. And if you analyze the stability and convergence according to standard methods, it would be better for you and for everybody else. Less wasted time. So Lendertzy decided to analyze the stability and convergence of his method. So he must have introduced the concepts of amplitude and phase portraits. That was 1965. Now in 1969, Cunge did the same thing, and I'm pretty sure, I could be wrong because I'm not perfect. I'm pretty sure that Cunge already knew the work of Lendertzy. We can check that easily, but I'm not going to do it now. If Lendertzy's paper is referred in the Cunge. But now, as I remember, Cunge only had four references. So maybe Lendertzy was not in Cunge. It doesn't matter whether Cunge knew Lendertzy. Cunge did it. Cunge came up with the amplitude and phase portraits. Besides, this stuff, I don't believe was Lendertzy's invention. I think Lendertzy brought this stuff to hydraulics, which is different than inventing it. It's like the herd analysis and all these other things, okay? We bring stuff into hydraulic engineering, from the mathematicians, who are technically the ones that develop the stuff, but they develop and they don't use it. We use it and don't develop, because that's just the way it is in the real world. Okay, so long story made short, Cunge developed the amplitude and phase portraits. But in typical Cunge period, I hope he's not listening to me, he made a few mistakes, and his presentation left something to be desired. I knew that from the beginning. When I read Cunge, I said, boy, he should not have done that. He should have done it this way. He should have done it that way, because we had experience. I read Cunge in the year 1977, and I already had 4 years of working at CSU and learning this stuff every single day. Remember, I told you that one day I forgot to sleep because I was so excited about this stuff. Okay, 7 o'clock in the morning, had worked all night, and then I took a shower and went back to work. My wife remembers that day, somewhere in 1974. Okay, so Cunge did this, and no, I'm sorry, Cunge did it, but he did it in an incomplete fashion. So we decided to do it completely, thoroughly, for everybody to see, for anybody around the world to check Vavia's calculation. So they will not be able to say, oh, where'd this come from? We don't know, and we suspect that you made a mistake. Because that's typical, by the way. If you have a very complex calculation, people are going to suspect that you made a mistake. And that is correct. If the calculation is complex, the chances for mistake increase, sometimes exponentially. So long story made short, we're going to go in here and talk about this paper. Comprehensive review of the amplitude and phase portraits of the Muskingum-Cunge, which Cunge did not complete. A flat routing is accomplished. The expression of the amplitude and phase portrait's convergence ratios R1 and R2 respectively are developed as a function of spatial resolution, Courant number, weighting factor. We actually wrote a paper on this in 1979. So this is really a kind of rehash with the idea that we got to do a calculator on the web so you don't have to run these messy equations in order to do this. I mean, it could be done all readily on the web, right? So it is concluded that the Muskingum-Cunge is a good representation of the physical prototype, provided that the spatial resolution is sufficiently high. I already said that the other day. You should shoot for 100. Why? Because you have the computers that can do it. No longer is it good to choose for 20 or 30. It's too short. Second, the Courant number. No, the spatial resolution is high. The Courant number is close to 1. Okay, 0.9, 0.7, 0.1, or 1, 1.0, 1.3. Don't use 4. 4 will lead you to errors. Don't use 0.1. 0.1 would create havoc in the computation. Why is that? Because 0.1 will give you instability. Any fool can see the instability. You, your boss, anybody, okay? 4 will not give you instability. They will give you lack of convergence. In other words, instead of getting an answer which say 100 is the answer, it'll give you 50. And if you don't know that you're non-convergent, you'll take the 50. You'll say, oh, the computer gave it to me. No, it's wrong. Okay, that's called lack of convergence. So the great number in excess of 1 will give you lack of convergence. And the low number will give you lack of stability. How do we know that? Well, because we tried this many, many times. Besides, the amplitude and phase portraits that we're going to show you today exactly repeat what I had just said. The weighting factor is high enough, better in the range 0.3 to 0.5. This is kind of a discovery of this methodology, by the way. And besides, remember I told you Monday that while we were clear on the C, we were a little bit unclear on the D, because of the way we used it that did not allow clarity at the time when we did this 40 years ago. But then, let me have a sip of water here. Then we came up with this. In this answer, we did everything. I mean, we did everything exhaustively, better than what I had done before. So we were able to see more clearly what was going on. And now from this paper, we could say that the weighting factor should be high enough, better in the range 0.3 to 0.5, which matches what I had said earlier the other day when I said the weighting factor should be around 1, but if you do it a little bit less than 1, it's better. I don't know if you remember that, but I did say that it should be, that we had no problem with D equal 1, but D could be 1 or even less, a little bit less. In this case, we're saying 0.3 to 0.5 would give us less than 1. Actually, 0.2, 0.3 for the D, for the cell Reynolds number. Okay, so we got in here amplitude and phase portraits originally developed by Cunge, expanded for the generalized convection problem. Okay, I quote my paper that we're going to read later on. Analyzed to stability and convergence. The Muskingum-Cunge method we already know. The derivation of equations we already know. All these equations are already known repeatedly in times. Okay, here we go where I ask you to sit tight and hold on to your seat, because now we are going to apply the Cunge method, which is the equation number 5, okay? It's the von Neumann expansion, Fourier series expansion, equation number 5, and we're going to do it in the discrete domain. Here, 6, 7, and 8. Can you see that? 7, 8, and 9, and 10, and 11, and 12, and 13. I'm not joking here. It looks like I'm, but this is ridiculous. We have done this when we were young. We can't do it anymore. I had Vavia do it because Vavia was clear in her mind and she could do the mathematics. And it took her 2-3 months to do this kind of work. 13, 14, 15, it gets thicker and thicker by the second here. The third term, 17, 18. You may think, oh, this is ridiculous. Well, it may be ridiculous, but at the end, you're going to like it because it's going to tell you everything. That's the beauty of math. Okay, so we got 21, 22. Look at these equations. 24, 25, 26, 27, etc., etc., etc. And finally, we get 37, 38, the solution of equation 40. Spiegel. Spiegel is the famous book, Shams outline. You all know Shams outline. We get to get that answer in there. We get the imaginary domain. And finally, we get the convergence ratios, R1 and R2. Those convergence ratios that I identified in my original paper, 1979, which we'll review later on in more detail. R1 and R2. Okay, in summary, given only weighting factor, spatial resolution, and Courant number, equations 48 and 51 enable the calculation of the Muskingum-Cunge amplitude and phase portraits convergence ratios. The calculations using the calculator. Okay, what is an amplitude and phase portrait? It is well, I'll show them to you graphically. It is a plot of the R1s and R2s for the given Courant number and spatial resolution, which are the two parameters. But however, what is an R1? An R1 is the ratio of the physical to numerical. I'm sorry, numerical to physical. And R2 is the ratio of the amplitude of the Fourier expansion, the amplitude. And the other one is, the R2 is the celerity. So it's telling you how fast the wave should have been and how it wasn't. And the first one is telling you how high it should have been and it wasn't. Any deviation from one will get you an error. So then the question is how different from one it is. So we plot it. Now this is the light. The light is coming now because you don't have to go through those equations. We already calculated and plotted them for you. Okay, so this is the R1. So this is the Courant number. This is the resolution. Very important that we look at 100. Don't look at 20. 20 is bad. 40 is still bad. My position is 100. So we go in here, and for Courant number of 1, it's coming up with 99.5%. Can you see that? 99.5%. And in here, it looks like the lesser Courant number is going to be better. It looks like that, but it isn't, because that's not, R1 is not the only thing. There's R2 in there, and then there's X, because these are plotted for X equals 0. But for some other X, it may be different. So technically, you can figure out those three and calculate your very own R1s and R2s that you can live with. So that's the advantage and beauty of this thing. No longer are we blinded as to how accurate that is. You see? R2. That's the R2 for X equals 0. Okay, then the R1 for X equal 0.1. So we cover the range. Remember that look at only the black, only the 100. The others are not to be considered. We put that for completeness, okay? Then X1, likewise, they're kind of similar, don't they? No, they're kind of, this one is like concave and this one's convex. Amplitude and phase portraits are for 0.2, okay? Then 0.2 in there is getting better and better for 0.3. Now all of a sudden for 0.3, the stuff starts misbehaving. The red went up. This also went up. The others did not go up. But if you use this, technically, if you use the methodology with X equal 0.3 and the red, you're gonna get instability right here. Because the R2, the R1 is not unstable yet, but the R2 it is. And is giving you some instability in there. More than one. It should not be more than one. Amplitude phase portraits for 0.4, same thing. Now it gets worse, 0.4, right? And then for 0.5, it continues to get worse. But as you can see, for the gray value, it looks better. It looks perfect. For 0.5, 0.4, look at 0.4. 0.4 is almost perfect. At 1, not anywhere else. That's why we say that in the vicinity of 1 over here, the method works well. Case proven. The method works well. We also tried 0.6, and 0.6 was misbehaving even worse. The 0.6 gives you an R1 negative, meaning that's going to, all of them are negative. Even the 100 is negative, which proves on what Cunge said, that McCarthy, that you should not use a method, Muskingum method with more than 0.5 because you'll get wrong answers. And that's proven by this methodology. You can see that. I didn't run 0.7 because it was not necessary, because nobody in the right mind is running Muskingum above 0.5. So we figured we could run 0.7. Okay, so that's the analysis, okay, and the practical applications, and I'm going to run in here. Oh, we have two methods, one for the general calculation and another one for the practical, because we want to give tools out there. Align Muskingum-Cunge convergence practical. Okay, so in here, we are going to say, oh gosh, okay, here we go. We're going to run this with velocity 1.75, mean velocity, mean depth 2.3. So velocity 1.75, mean depth 2.3. Let's assume that those are problems that you have, okay? Slope of 1.3 here, right? Yeah, 0.013. 0.013? No, 0.0013. Let me double check that. Yes, that's correct, 0.0013. That's an average slope, by the way. Most real world applications are on the order of 0.001. I put in 3 in there to slightly be different. 1.6 is the standard almost trapezoidal channel, because 1.67 is rectangular, 1.55 is real trapezoidal. Floodway rise, the floodway is 24 hours, reach length 4,800. Okay, we'll go in here 24 hours, reach length 4,800. Okay, 4,800, and time interval 0.5. So time interval 0.5. Basically, what we're going to do is we're given some algebra in here with the formulas that are given to the right, and the formulas to the right are the physics, and then the formulas that come from the numerics are there in the reference, and now we're going to do the calculation to find the R1s and R2s. Okay. The R1 is 0.999 and the R2 is 0.99999. How could you improve this? You can't. That is why the Muskingum-Cunge works well. Because properly used, it will give you perfection, close to perfection, 4 digits accuracy. 1 is perfect. 0.999 is 1 per 1,000. 1 per 1,000 in engineering is nothing. Okay, so I've proven to you that the Muskingum-Cunge works. So finally, we got 10 minutes. I think it will be, we will do fair to my friend Ferrick. I met Ferrick in it would have been 87, roughly 87, because I visited the Krell lab in New Hampshire, at Dartmouth, by the way, Dartmouth, somewhere out there, New Hampshire. It was in the winter. I almost froze to death to get out there. Being from California, I wasn't used to cold weather. Although I've lived in Colorado, so I shouldn't complain. But out there, it was cold. And they have the Cold Regions Research and Engineering Lab out there. So I talked to Ferrick. And I don't recall whether I talked to him before he published or after he published. I think it was after he published, because I realized that he was a good guy. Okay? But like everybody else, nobody's perfect, right? So Ferrick made a mistake in here. Not a mistake, he just didn't do it completely. Excellent researcher, in my opinion. I'm joking here. He didn't do it completely. He derived the third order dispersion equation, which was something I wanted to do and had not been able to. And he gave us the way to do it. You figured out this and this and that, you combine the equations, da-da-da. So you have to read this stuff. He was doing what he called unsteady flow in tailwaters. Tailwaters are in canals. When you operate gates, you end up with flow that is Lagrange, but not quite Lagrange. In other words, something coming down on the S-curve. And that was his job, that somebody told him to do that in the lab. So he did this. I'm sure he spent a couple of years writing this paper. It's a very good paper. I'm not going to request that you read it all because it's not necessary. But I'm going to talk about it because what he does say is important for our work. Okay? Besides, we had a paper written based on what he did, only that we improved it. And we're going to talk about that later. Okay, so he basically is going to take a problem that is not quite dynamic and not quite Lagrange. It's kind of in the middle. So he's going to solve the equations of open channel flow. Whether he solved them in a set of two or he solved them in a set of one, that's his problem. Remember, the Hayami used only one, while Liggett and Fred used two. Presumably, it's better to use two because the one implies linearity. The two does not imply linearity. But that's a different story because the linearity is something that is quasi-linear anyway. Okay? So the point that I'm trying to make in here is that Cunge is a good guy, and he came up with this equation number 2 in here. No, I'm sorry, it's not the equation number 2. Equation number 3 is the one that he got, where he combines the equations, which I did in my other paper that I'm going to be talking about it later. And he gets the first order equation, the second order equation. This is Cunge. I'm sorry, not Cunge, 7. Are you seeing what I'm circling here with my mouse?
Yeah.
Okay. This is 7. This is 7 right here. Okay. This is Hayami. Okay. This is Hayami, and this is Ferrick. But Ferrick is combining these. You can see the second derivative of q with respect to the dx squared dt. No, to dx dt is the second derivative? I think it is. And then the third derivative. Yeah, but he's got to get rid of this, otherwise he won't be able to make it. So finally, he ended up, he manipulated these equations and ended up with C, which is the seventh speed, D, which is the Hayami diffusivity. Actually, not the Hayami diffusivity, the hydraulic diffusivity, which could be either kinematic or dynamic. If it's Hayami, it is only Q over 2B S of O. But if it's dynamic of Doog, Doog is the one that can contribute this equation. This one here was contributed by Doog. Interestingly enough, I asked for the homework due today, for the essay due today, what was Doog's contribution? And I received half of the answers already, and the answers didn't focus on what I had intended to. But I have to understand that not everybody reads my mind. And then I said, what was Doog's contribution? I mean, Doog had so many contributions, you could pick any of them and sail with it, right? So I'm not going to mark down those of you that said that Doog was a great guy. But Doog's contribution in my mind is this equation over here. He improved on Hayami's equation. This is Hayami's and this is Doog. Okay? If you wanted to redo your homework, you're certainly welcome to do so. The deadline is tonight at 10, but you don't have to do it because that was after the fact. Those of you that have not done it may think about it, okay? But the point is that this was Doog's contribution. This is what I wanted you to say. But I wasn't exactly clear, so I'm not going to penalize for you. Okay, because like I said, Doog had many contributions. Okay, so this is the D. So this has got to be the third order dispersivity coefficient, which is the contribution of Ferrick. Okay. However, Ferrick made a mistake. Note that this equation is not dimensionless, it's dimensional. Okay. So then he proceeded, like everybody else, he wanted to get dimensionless. Okay. And here it is. Here it is. He's going to now figure out a way of doing dimensionless equations. But he came up with this. He said Q star, which is dimensionless, is equal to Q over Q naught. X star is equal to X over delta X. He made a mistake in here. He did not dimensionalize according to the XS type curve rule, which involves the U sub L and L sub L, U sub O and L sub O. The L sub O is fundamental. So when I saw this, I said, Ferrick, my friend, you messed up. Well, you didn't complete it. You didn't mess up because you illuminated other people like me to where the problem was. Because otherwise, had I not read Ferrick, I probably would never figure it out. We have so many things to do anyway, right? So I said, there's room in here for improvement. So I proceeded to do that, and I ended up with a great paper on the dimensionless dispersivity, by the way, which we will talk about later on, in more detail. So these equations are not complete. They're not complete. So that's basically what I was going to say about the Ferrick paper.